There. All right. First one, collect your MATLAB. Let me get that from everybody. Just, why don't you do it this way? Hand it this way. Make sure your name's on it. I need the code and the plots. Make sure your name's on it. And if you can staple together, put down here. Then when it gets to that side, bring it up front, please. And just set it right here.
I don't know how to do that. Grid on.
It's grid on, hold on, grid on, yeah.
I mean, hold on just means that you like put other lines on top.
You could, if you have multiple plots, it will overlay the plot on the same figure.
But it in this
Doesn't
case,
have the
since there's
figure.
only one line, it doesn't really make any difference.
You do plot whatever, hold on, plot whatever, hold on.
Well, no, you have to do only one for the beginning of the code that holds it for the entire run of the code, yeah. Like, you don't, it depends.
Is it also like different
Yeah,
fonts as well?
you can.
It's like, I'm a little confused. This time it's gonna dump the first part of it, and that's gonna be how big is the stuff.
Oh, yeah, that's why.
After that, be the stuff. I don't walk that guy.
Do you know what the command in MATLAB is to break out of it when operation?
Let's do towards control. Yeah, there is a specific one.
I know there's a command, I just don't know what it is.
It's not quit.
The,
Quit closes everything.
no.
We may need a quit in this one. This thing, what happened was it had a counting problem.
You can quit debugging up there on the terminal.
Oh, I know what happened.
Oh,
My
yeah.
thing, I have to do this secure CRT thing.
It's not. It's, it doesn't
If I don't
show
do
you
that, I
players.
can't do
It's-
that.
This is that.
Yeah.
Honestly, it didn't work.
Have you used it?
No.
Oh.
My Dr. Wall uses it.
I see. Okay. I was just gonna say that would be smooth that you said.
All right, here's what I wanted to do. I wanted to talk about a couple of things. I'm going to answer your questions in a second, but I want to show you Gibbs phenomena. Remember, I mentioned Gibbs phenomena when you have discontinuities. I'm going to put a waveform up there, and I'm going to discuss the percentage of Gibbs phenomena and how the actual value of the Fourier series goes to the average of the two spots just at the discontinuity. So if you're at 5 and 0, then it would be 2.5. That's where it's going to converge to. But it will bounce to get there. And there's a thing on Wikipedia about why it does that. Let me get one that does it first. Get rid of that one. I think everybody knows you just change this coefficient basically because I've given you the program to do it. So I think this one has a discontinuity, but I'm actually not sure. The average value is going to be off on this. And the average value, I forgot what it was for that one. I think it's divided by 4, so this is going to be divided. X0 is that divided by 2 times T, I think. I hope I'm right. Let's see, I'm just trying to get the waveform so I can talk about it. All right, now let me blow that up and talk about this. This is Gibbs phenomena, and I really don't like using PowerPoints, but here it's beneficial. You see this overshoot here and here? Now, you see ripples here. That's always going to occur to some degree, whether it's observable or not. The more terms you have in the Fourier series, if you count, say, the first 10, in other words, you have C0, C1, C2, all those C10, you'll see ripple. You count to 100, goes way down. Count to 1,000, you can't even see it, but no matter what you do, this will always occur, this overshoot, if one of your points that you're going to actually do the tabulation is right at the discontinuity. Now, I kind of forced the issue here. So what I want to do is, and most of you probably have, how many played with MATLAB or Python saw this? It doesn't matter what language. All right, you saw, how many did the MATLAB assignment? Let's try that. All right, if you didn't do it, please try to do this. This is for your benefit, it isn't mine. All right, this is something you have to know, yeah?
Is that the same thing that because I've heard of ringing, is Well, this is ringing caused by a mathematical aberration. Ringing, usually in circuits, is an LRC type of ringing, and that has to do with physical energy, capacitive and inductive energies being swashed. But this is, yeah, it is ringing, but not caused by the usual source. This is caused by mathematics, nothing more than that. Or I should say, in this case, a computer algorithm that's displaying the mathematics. Now, if I go here and I change the number of terms, I have M100, and if I go to 500, by the way, that's a big calculation. Something we'll talk about later is how to take this from out of a for loop into a vector operation. It makes it streamlined, but I'm not going to do it right now because you won't see the beauty of it. I'll watch what happens here. Now you can see that those bumps are just about in the noise. You can't see them. But one thing for sure is that discontinuity is there. And that's an 9% difference. If you took the range from here to here and multiplied it by 9%, that would give you the range, the additional range that you see there. Follow me? So both top and bottom are about 4.5% above or below the actual norm that it should be. Remember that. And you cannot get rid of this by just increasing the number of terms. Now, in the limit, if there was a theoretical way to do an infinite series, in fact, it would go away. But you can't do that. And you can read about this on Wikipedia if you're interested. Right at this discontinuity, the actual value it converges to is 1/2 that. At the discontinuity. The problem is you can't see that displayed there. But I think if I put dots or stars, you'll see it. The problem is if I do that, because I got 1,000 points, it's one big fat line and then a dot in the middle. So that's that one. Now, was that the one I asked you to do, I think, right?
Yeah.
All right. That one shouldn't have been much trouble because you literally had the value for C of n in the answer that I gave you, right? So you just had to take it and put it in here and do your plot. And that was sort of a gimme on this one. All right, now, before I shut down MATLAB, were there any other questions about MATLAB per se? I'm going to just mention a few things since I've got you here. And I'd like next week, one day, how many have laptops in here? Do you have one? Do you have one or not? You do? If you could bring your laptops in one day, say Wednesday, I would like to go through some of the tricks with MATLAB. I'm going to give you another assignment in this, and it's not for my benefit, it's yours. One of the things is, I don't use Python, but I'm going to start. I know MATLAB, that's what I go to. There's a couple of things I have to tell you right now so you know if you're playing with this, you don't mess up. There are vector operations, and then there are individual, they're called scalar operations. So let me show you what I mean by this. If I say A, I'm going to create a vector A. First, I'm going to show you something. Suppose I just want to populate with ones. I can type ones, and now the dimensions of the vector 2, or this is a matrix, say 3. You don't have to write this down. You don't need to write, just pay attention. It's recorded. I'm going to go through this again, but I want you to just watch this. All right, now you see that's a 2x3 matrix, right? It's 2 deep vertically, 3 across, right? If you wanted to just find out what the values of them added up column by column, so 1 and 1, 2, 1 and 1, 2, 1 and 1, 2, you could type sum, now just look, A, and you have 2 dimensions. The first dimension is summing them downward, the second is summing them across. So if I have 2, 1, you watch, you see it's all 2, 2, 2. Everybody? If you want to get the last command back, you just hit up arrow. And there it is, and there's ones and so forth. You follow me? Now if I want that command, but I want to modify, and now let's go over by 2, you all see it's 3, 3. Can anybody see that in the bottom of the screen, guys? Or not? Let me try to make sure you can. It's down here. You all see what I'm talking about in the back? Now, the number of dimensions in A is unlimited. Right now I have 2. You could have 3 dimensions, so you would have depth. 4 dimensions is abstraction, you can't see that. But you can have as many dimensions as you want in a matrix. You can have a 1, you can have a 1, or say you could have a 2 by 2 by 2 by 2, which would be something visible. It would be a 3-dimensional cube, all populated 2s. And then in the next dimension that's invisible would be theirs too. Now we use this a lot of times for signal processing work, and I'll tell you this much. You know how right now you're familiar with, you're going from you're going from time to S, right? You've done that. Or time to frequency. Well, you're gonna see time to S, right? You're transforming time into the dimension S, and S has a real and imaginary part. You can also transform spatial dimensions. X, for instance, if you have a function that's a function of X, maybe the height of something versus that, you can go ahead and transform that by an e to the effective minus sx, or it doesn't have to be s. Usually they use minus jk. K would be the symbol for the first spatial dimension times x. Do the transform. Now you got a function of just k. You follow me on that? And they do this typically for analyzing. What was the one real benefit of doing Laplace transforms? I mean, there's a lot, but I mean, just think of the one single thing that you overcame that you probably should learn to hate besides convolution. You didn't have to solve differential equations with integrating factors, right? You ended up with what? Algebraic equations that you do partial fraction of to get back to the time domain, right? It made life easy. Well, when you're writing differential equations that are spatially varying, second derivative of E field with respect to x squared plus second derivative of E field with respect to y squared, that's called a Helmholtz operator, plus second derivative of EX with respect to z squared plus some k squared, E's equals 0. Now you do transforms in spatial dimensions, and then you solve that differential equation in a transform domain, but it's just like the Laplace transform, all right? And that's the thing I'm going to tell you about. Remember to keep this in the back of your mind when you're exposed to this. Your senior level courses, they'll take you through it probably indefinitely if you take some advanced courses in either EMAG or communication theory and things like that. You're going to be exposed to it. But you heard it here first, so you don't panic when you see that. It's not a hard thing to just understand the dimension you transform from can be anything. Time to us represents tick-tock, right? T could be anything. It could be a length, it could be a weight, it could be anything. Follow me on that, guys? All right. Any other thing before I shut this down? All right. Now, next thing, questions. I have what I want to do. Was John Hung teaching in here just right before? Does he use this, he writes here? I don't know how he does it. I don't like writing that thing, I used to. Get my stuff. What happened to it? Didn't we have a clock in here?
It fell apparently in one of the classes down here.
All right, would you do me a favor? Somebody yell at me when it's, I got 10:14. When it's 10:35, all right? And just interrupt me. It's one thing you should feel free at. And I try to encourage people. What I mean is, if you interact, time passes and you remember things. If you just climb up and, get on your cell phone, it's like, why be here? In fact, I was in a class one time, it was an economics class, and I'll never forget this. A fairly bright, little arrogant student was there, and the teacher we had was like premier in economics. And he was giving a lecture, and this guy pulled out a newspaper, he's reading, and he's ruffling the pages. And that professor laid into him like I've never seen. Anybody ever seen a professor go after a student? All right, I mean, this guy wishes he was dead after that. They really got after him. But what I'm really trying to tell you is, I don't care if you have to text or something. Please try to spend the majority of your time paying attention, because you're paying for it. Now, questions? Yes?
So there's a problem that we did last class that I
Which
was
one?
confused on.
Which
so
one?
It's from homework 13. It's a triangle.
All right, help me out here. We'll do it right now. Which way does it look?
It's a right triangle.
Is it going this way or is it going this way?
Positive sawtooth.
All right, this way, right? Is that it?
Yes.
Let's do it. Why don't we call this just tau, or t, tau here, and this be t, and then it repeats itself, right? Is that right?
It's just back to back to back to back. There's no space.
Oh, okay. All right.
Yeah.
Yeah. This is a good one. Thank you, because this brings me up to my next point.
Okay.
It's perfect. So, this is the x of t. This is a good one. It's like this. So this is just t, not tau, right? 2t, 3t, and so forth. And let's just call this a. And that way it's arbitrary. A and t can be anything. We don't have to put microseconds, nanoseconds, or whatever. Now, when we do this, the way I recommend you do it, you could do it by integration by parts, because I want to take this x of t, And I want to go ahead and I would like to get x of t equals a summation from n equals, gotta know this, minus infinity to infinity of c of n e to the j n omega naught t, where c of n equals 1 over t, the integral from 0 to t, of x of t, right, times e to the minus j n omega naught t dt. I know that's fast, but you've got that already. That's just the definition of c of n, right? Fourier coefficients. I like to do one other thing too. I'll put epsilon, I'll put minus epsilon here and t minus epsilon. And you can adjust epsilon, it just shifts the window so you're not there when the discontinuities take place. Follow me, guys? That's it. Now, you could do that, and this, and that operation there would be an integration by parts, because this function right here is given by x of t is the slope a over t times t from here to here, right? So you could do the integration by parts, and we did that one time, right? It took a little time. But the way I suggest, and you're foolish if you don't, is just do it with derivatives. But before you do derivatives, and this is the point I'm getting at, before you do it, the derivative method will not capture x naught. Do you all understand that? It does not capture the average value. So before you do anything, you need to break out C0 as 1 over t, the integral, in this case I can go from 0 to t, of just x of t dt. For this one, it's obvious. We're integrating the area and dividing by the period, right? Now, I think everybody knows that when you deal with a right triangle, the area is the width times the height divided by 2. So when I do that, I can say C0 for this one is going to be tau A by 2, and that's it. There ain't no other thing, right? Now you've got that. Now to get the other C of n's, not C0, we take a derivative. It's important to see this. We take one derivative, and our first derivative does what? Well, since these are back to back to back, you've got to be careful. I'm going to work from 0 to t right here, and I want to make sure you see this. Got me, everybody? All right, watch. You take a derivative with respect to time. I'm going to start right here. You see it went from a to 0, downward negative. It's a delta function. Everybody? So here, you're going to have a delta function. Forgive me if you can't see this. It's minus a delta t, right? Now, immediately after that, what happens? Now I've got a constant slope. So now I've got a term here that's just dc. That's supposed to be a constant. And the value here is a over t. Do you all see that? That's the slope of the line. And what happens here? Bang, another delta function, then a constant, right? Come to this 2t, another delta function, but the delta functions all occur where the pulse starts again, right? And they're negative. Now here's what you do, and listen to me carefully. You break this into two functions. Your first function, right, I call it x1 of t, and then put a prime there. That's just the sum of delta functions from n equals minus infinity to infinity of minus a times delta of t minus nt. That's a mathematical statement for this. As you're summing, everybody knows this is a sum sign, right? With n, if n equals 0, you get minus delta t. That's the first spike at the origin. N equals 2, it's the second delta function, minus a, right? N equals 3, the third. So this right here describes what I'm drawing here. But that's the first function, and I put a prime here, right? The second function, x2 prime of t, is just equal to a constant. It's a over t, period. There's no variation. There's no u of t or p of t or sum of anything, right? That's what it is always. Got that? Does everybody follow me on this? I'm going to break it into this delta function plus this. That's what I'm seeing here. Now, here's the interesting thing. What happens when I take another derivative on 2? It's 0, right? So that means the c of n's, c2 of n double prime are 0. How do you go from there backwards if I wanted what it was for c2 of n prime? You would take this divided by j n omega naught, right? 0 divided by anything finite is still 0. And we do not use the n equals 0 term because that's done here for us, all right? And if you divide it by another j omega n to get to the actual x of t, x2 of t, it's still 0. So in other words, that goes away, and I hope I'm answering your question. Does everybody see this? Yeah. Did you have a question? No. All right. Everybody on this one? Okay. Now, what happens here? Well, now I've got my x1 of t here, right? Prime. So I'm going to go get my cn1 prime, the coefficients, right, guys? So let's do it over here. I come over here, and I say now, my cn1 prime are equal to 1 over t, and technically it's the integral. I can go from, I'm not going to go from 0, I'm going to go for some minus epsilon to t minus epsilon here, where epsilon is very small. And then it's going to be of x1 prime of t times e to the minus j n omega naught t dt. Now what that is getting the Fourier coefficients for a Fourier series representing those delta functions. Got me on this? Right? All right, when we take a look at that right here, what is that actually though? That's 1 over the period, right? That's arbitrary. Then I have the integral, and I have from minus epsilon to t minus epsilon of this. What is that? Well, that is a sum of n equals minus infinity to infinity of, in this case, minus a times delta of t minus nt times e to the minus j n omega naught t dt. Now, I put the summation in there for a reason. Does everybody see what I've done? How many understand what I've done there? I've simply taken the mathematical description for these delta functions and placed it inside the place where I do the operation. Y'all see this, guys? Can you see it or not? No? You don't see it? All right, remember, this is a delta function series. I'm labeling this delta function series as x1 prime of t. Got me on that? Right. Now, if that's a delta function series, it can be represented this way. Do you all agree with that? Give me 1 second to finish my thought. Do you agree? Now, what does it say? If I want the Fourier series for x1 prime, I have to get the coefficient. So I put in x1 prime of t right there, and I multiply by e to the minus j n omega naught t to get this value, right? Here I simply replace x1 prime with the mathematical definition, right? How many see it right here? I'm going through this stuff sequentially. Now, the one thing about this, what's the only term here that matters? If I'm going from 0 to t, the only delta function I care about is that t equals 0, isn't it?
Yes.
All the other delta functions are outside the range of integration. You all see this? And remember, I'm going to slide that window. The window really says from here to here, but what I'm going to do is slide it down here so I go over a period from here to here and only capture 1. So now I can say, really, I just need one delta function. What delta function do I need? I need the minus a, right, times delta of t. Agreed, class? You're going to see the beauty in this. Now remember, that's the prime, correct? What is the value of that integration? By inspection. Well, when does the delta function turn on? 0, right? What is the value of the functions adjacent to it at 0? 1, right. So this whole thing becomes simply minus a over t, and that is c of n prime. Just take a look. Do you agree with me? That's c of n prime, right? For any value of n, correct? Doesn't matter what n is.
Can you explain that one more time?
When you integrate a delta function, what do? You find out where it turns on, right? You agree it occurs at t equals 0. So you stick 0 in there, right? You extract the value of the function. Well, e to the 0, no matter what n is still 1, correct? E to the 0 is 1 for any value of n. N times 0 is still 0. Correct, class? So that's what this is. Now, we're not done yet, and this is, I should put 1. How do I get the value of c of n? 1.
Divide that by
J.
J.
Right.
Omega naught.
So I take this divided by j and omega naught. And now I have my Cn1. Now, if you think about this, my original x of t here that I represented, now that x of t, I broke down into, the x of t was some x1 of t plus x2 of t plus x0, and that is the average value. You all follow me? What was x2 of t? 0, goes away. What was x1? Minus a, right, over t times j n omega naught, right? It's that. And that is the C of n, but actually I didn't put the series in. Technically the series would look like this. It would be an infinite sum, n equals minus infinity to infinity, of C of n, that's minus a over t divided by j n omega naught, correct class? Then that's C of n, it's times e to the minus j n omega naught t. Agreed? Now that's the exponential Fourier series with a coefficient stuck back in there. And that is correct. But I don't ever use that mathematically, on computers for any simulations. I always turn that into the cosine series. You remember I told you about that, and this you have to know. I want to spend, does this answer your question?
I'm a little confused why x2 of t is 0.
Well, when I take the first derivative, this is x2 prime, right?
Yeah.
Do you agree it's a constant? Take a derivative of a constant with respect to time. What do you get?
0.
All right, 0 divided by j and omega naught is?
Oh, that, okay.
Got me?
Yeah.
So in other words, once you got a 0 there, it's forever a non-functional thing. You don't worry about it. Agreed, class? Now, when I take a look at this problem, this is an excellent problem. It really exemplifies a lot. It shows you how to deal with some of the things that are oddities. We got delta functions just at t, right? So we adjust the window. The other thing we got is, when we got this first derivative gives us two functions. We turn x of t into x1 of t, x2 of t, and we find out what x1 of t and x2 of t are. Turns out x2 is 0, and x1, by dividing by j and omega naught, is that. Yes?
For your the first time you wrote x of t, you had cn times e to the positive j and omega naught t, but this time you wrote it with a negative. Is there
No,
a reason?
no, it should be a positive.
Okay, all right.
That's an error. The series has always got a positive j and omega naught. The integration to get that constant has got a minus. Now, to be frank about it, you could reverse those things and it would still work. If you got one positive and the other negative, it doesn't matter, it works. Trust me on that, but I'm not gonna prove it. Now, I've gotta go and do one other thing, if it's important. I've got a couple things. We're gonna take this first, and I'm gonna remind you the cosine series is the one that we use all the time. Does anybody else have a question about a problem before I move on to this?
Do we also need to add like x naught to that?
You do. You do. It's this. Technically, I didn't say n unequal to 0, but I should plus x naught. All right, and this you have to know. I mean, you've got to know this, period. I can't say that with enough emphasis. Now, remember what I did last time to recoup, and the day before that even. I said that if we have x of t equal to the summation of n equals minus infinity to infinity of c of n e to the j n omega naught t, right? And I'm going to leave it like that. I'm going to say that when we go ahead, when n is equal to 0 here, this is just 1, so you get c0, so I'll leave it alone. All right? Now, the next thing is this can be broken out into a single-sided series where n equals 1 to infinity of 2 times the magnitude of c of n times the cosine of n omega naught t plus the phase angle. I'm using c of n. You're actually used to x of n. I'm sorry about that. My other course, I'm using c of n. X of n. They're the same exact thing, just a different symbol. Do you all remember that? That's a cosine series, right? A couple of things I want to show you. In the book, he has a sine and a cosine series with different coefficients. So I want to make mention of something that I'm going to use to turn it into their series, whether it's called a trigonometric Fourier series. Do you all agree that, if you don't worry about it, cosine A plus B is equal to cosine of A, cosine of B, minus sine of A, sine of B? That's a trig identity that we can prove at another date. It's very easy to prove if you use Euler's. That's just common, right? Now take a look at what I got. I got cosine of A being n omega naught t plus B, angle of C of x of n, right? Follow? So what I'm gonna do is this, I'm gonna say this series right here can be rendered, and by the way, I'm gonna go ahead and put the x0 there, that has to be there. This can be rendered as n equals 1 to infinity of 2 times magnitude of x of n. And now instead of this cosine business, I'll take cosine here of the angle of x of n times cosine of n omega naught t, then plus, or I mean minus sine of the angle of x of n times sine of n omega naught t. I'll replace that, and I'm going to take plus x of 0 out there. You all see I just replaced the cosine of omega naught t plus the phase angle with the actual trig identity. A was n omega naught t, and the phase angle was really b, right? You all follow me on what I'm doing here? Remember that trig identity? How many do? You remember seeing it, whether you remember, right? You had to, where do you use trig identities? You use them calm a lot, you use them in, I think in calculus you had to use some of these things too, didn't you? Trig identities are useful, they're irritating though. And if you ever want a trig identity, this is a tip. If you have anything, cosine, sine, anything like that, and you want a trig identity, say you have this right here. Well, what is that in terms of exponentials? It's e to the j a plus b plus e to the minus j a plus b over 2, isn't it? Just do the, that's Euler's identity, right? You can go from there, and then you can factor out, you get e to the minus ja, e to the, e to the jb, sorry, e to the ja, e to the jb, e to the minus a, e to the minus jb, divide by 2, and you can actually manipulate that very easily to turn it into a sine and the sine cosine stuff. I don't have time to do it right now, but that's how I do all the proofs. I never memorized trigonometric identities that they have all over. That one I had to, because I use it too often. Now, in the book, what he does is this. Do y'all see here that I have a series that just has a cosine function, and I have another series that has a sine function. What's adjacent to it is 2 times the magnitude of xn times cosine of this cosine. This is like a single term right there, and it's a coefficient. When I take this times this, I get another single term, and this series can be rendered, and this is the one in the book. It'll render from n plus x0, n equals 1 to infinity, and there'll be a term a of n times cosine of n omega naught t. Then they'll have another series plus the sum from n equals 1 to infinity of b of n, that's an a, times cosine, or I mean times sine, pardon me, sine of n omega naught t plus x0. And I want to make mention of something. This a of n right here is nothing more than 2 times magnitude of x of n times the actual cosine of the angle of x of n. And this b of n is nothing more than 2 times magnitude of c of n times the sine of the angle of x of n. Now, what? What? All right, thank you. And what I want to tell you is this. If you have odd and even symmetry to certain things, you can exploit properties here. That's why they do it. I never mess with that, all right? That's my take on it. It's more work than it's worth. Just use the exponential series is what I'm saying. But you have to be aware of this and what these coefficients are relative to the cosine series. Yes, sir?
Did that negative sign in front of the sign just turn into the b of n?
It should be a minus there. B of n will have a minus, my bad. I don't use that thing, that's why I don't really focus on it. You all with me on this? Now, one last thing. I'll make sure I didn't miss anything in my notes that I covered. I did that. This is where we're going. I mean, Fourier series. You know, how many terms should I take? As many as you need to so the waveform looks like the original waveform. That's my take on it, right? You want to get close as you can. You know you're going to get the overshoot problem. You have to be aware of that, caused by the Gibbs phenomenon. So that's just one of them deals. And the next thing I'm going to say is, when we're doing this, our real goal is not to do this for the, this is my take on this stuff. When I was sitting where you are, I think we got an easy function. I know mathematically ways to describe it. Why don't we turn it into an infinite bunch of terms? It seems like a waste of time. Well, the real reason we do it is because each one of those terms, as engineers, we can turn in terms of a magnitude and an angle for a phasor that would be exciting a circuit. For instance, you had, and I've said it before, 10 cosine of omega naught t plus 30 degrees. You always, when you did circuit analysis, take it to 10 at 30 degrees, and you just use the J omega to find the value of the reactances, right? J omega L was the impedance of an inductor. 1 over J omega C was the impedance of a capacitor, right? Then you did circuit analysis just like you did at DC, only with complex numbers. Well, we do that with every single term. We take the magnitude and the angle of every single term, right? That's the cosine series. We know the frequency is n omega naught, so we get the impedances for not omega, but n omega naught. And we get a transfer function. Now I'm going to do this on Monday. Then we can get the output by multiplying the actual the series we have there, the cosine series, by that transfer function. And I'll show you what happens. And it's really neat, because now you'll see why we're doing all this. And you know what's coming, so everything off your desk.